Good morning, everyone. I am Daphne Montalvo, and I'll be the first reporter of Group 6 that assigned to discuss about model testing. We always see models in fashion industry that basically walk in runway. We also encounter artists, influencers, and other content creators in social medias and internet that these young generations are fan of. But are these models, influencers, and content creators bring good influence to these young minds? Same thing with business. Why there is a need to establish business model? Or what is the role of business or model testing in every industry? Why testing a business model plays a vital role in decision making of an entrepreneur? In this chapter, you will be able to understand all of this why, since the following objectives will be addressed that will help us to establish a good decision making when we put up a business in the future, and what's really in the model testing. You will also notice along the discussion with my group mates that there are specific tests and procedures you should follow to test the suitability of the model for your own purpose, to uncover flaws and allow improvements on the chances that your model will be used and useful. There are illustrations that show how the test can be applied and how failure to do so often results in absurdity or project failure. We often say that model is being good enough because it is validated, and sometimes it is because verified. But what these words mean? The word verify came from a Latin word verus, means truth. Verification has something to do with the process to ensure whether the developed product is being developed accordingly or not in the beginning of the phase. Meanwhile, validation is the process of validating the product whether the development is right or not during or end of the development process, where valid implies being supported by objective truth that each conclusion is said to be correct since it is derived from the premises given. In a system, verification means involves inspections, reviews, and walkthroughs where it checks documents, files, and even information. And validation means that validating the actual and expected output of the decision making. It is the dynamic process of testing the real product in making a decision. So as you can see in the diagram, there is interconnected loop between the two because by its definition, they both go hand in hand. In verification, you see the several tests, the automated integration and unit tests that mainly involve in walkthrough tests and walkthrough inspections, reviews that test the documents, files, and information. It gives you a guiding question of, am I building the product right? Well, in validation, there is this customer acceptance test, usability test that mainly validates the information gathered based on the response or possibly response of the customers that will help in testing the real product in making a decision. It will give you a guiding question of, am I building the right product? According to some authors, model is a fiction, and validity and verification is based on judgment. That other judgment might be different than the judgment of another. Reason that no model can be verified and validated because model can be wrong due to the changing environment time to time because of the judgment differences and based on the purpose and objectives of the company as well. To answer the connection between the two, a business model must undergo several tests, like regression, beta, and system testing, where information are being gathered through systematic and analytic statements or propositions in order to know whether you are creating right and you are right in creating it. That is why, in making a decision, testing the model is important. I made here an illustration that tests of any theory or judgment take with particular equipment and instruments. Experiments can never test the theory alone, but by formulating only joint hypotheses and auxiliary assumptions, that equipment is properly set up, that the instrument work as expected, and that there are no sources of uncontrolled variation. But in reality, no matter how carefully an experiment is done, an infinite number of possible sources of uncontrolled variation always exist. Therefore, there is always an infinite number of hypotheses that can be invoked to save any theory from this confirmation. From formulating assumptions, like you wanted to produce a product that will make you earn profit and satisfy your client, you have to formulate for assumptions. And then afterwards, you have to create wild guesses and answer questions about who, what, and how. Like, who will be your target market? What will be your product? How will you act to achieve your purpose? And how to address clients' needs? And is your business model suffice to answer these questions? That is why there is testing. We're testing based on equipment and instruments like regression testing, system testing, and beta testing that basically involves statistical and analytical information. Then, you can move forward to formulate and establish your business model that addresses your assumptions. Means all theories can always be adjusted to accord with any data whatsoever without discarding the core propositions. That is why validation in every step of the process and verification is present in the beginning, during, and ending of the process, and even throughout the process continuously because it is dynamic or it changes time to time. Your business model changes time to time based on the hypothesis that you formulated because of the adaptation of the said changes. So moving forward, I have here a second illustration. Like you are the founder team who visualizes in establishing a business model. It must undergo first customer development insight cycle under customer discovery, where I've already discussed or the same discussion in the previous illustration. So, and then afterwards, you have to go through with the customer development insight cycle before you adopt customer validation, where through customer validation, you will be able to know what will be your customers' needs and that your business model is suffice enough to address your hypothesis or your customer discovery assumptions. Moving forward, once undergone with the customer validation, there are questions modeled that can be used that serve as a guide by the model users or decision makers but neglected and not considered. Actually, these questions are designed to assess the overall suitability of the model that fit their purpose, its conformance to fundamental formulation principles, the sensitivity of results to uncertainty and assumptions, and the integrity of the modeling process. Here, these are just some of the questions that can be found in the reference book. For further questions, you can refer to the books in chapter 6 or part 6 rather. So to continue, in developing the structure and decision rules in models, knowing the types of data is one of the issues you can encounter in model testing. What are these types of data? Quantitative and qualitative data. Quantitative data can be addressed by numerical data, where this involves series and cross-sectional records in various databases, which basically termed as hard variables because it is intended to show that the numerical data are more accurate and real than qualitative data. While qualitative data involves written and mental data. Written data include records such as operating procedures, organizational charts, media reports, emails, and any other archival materials. And mental data span all information in people's mental models, including their impressions, stories they tell, their understanding of the system, and how decisions are made and stuff. It cannot be accessed directly but rather through the use of observations, interviews, and other methods, which basically termed as soft variables, for this involves goals, perceptions, and expectations. Another issue that you will encounter is documentation. We all know that documentation plays a vital role not just in model testing but also in our daily lives. This is about in our work where we have to be organized, we have to make or create a to-do list or checklist in our job in order to have a smooth flow of our day-to-day activities. But why document a program? Well, it's because through proper documentation, you can come up with a good result that can be understood, replicated, criticized, and extended by others. Detection of errors and flaws can be easily detected in every aspect of the process. That is why we have to document not just our daily activities, but also in engaging model testing, in engaging flowchart or program in an organization. That was about my report or on model testing. The introduction about what model testing is, what is the essence of validation and verification in establishing a model in our business model. So let us now go back to our objectives and let us think if we really met these objectives in my report. First is we are able to understand that establishing a model is based on our purpose in our objective as an entrepreneur. We also know that model cannot be validated nor verified due to inevitable factors along the process. Let us also bear that in order to achieve effective business model and efficient testing model procedures, always consider those pragmatic questions that decision makers must look into to answer some issues like how to gather information, use this information based on its type, and create a good model testing process. The progress and the flow must be documented to understand and reconstruct just in case there are changes or flaws or errors detected along the way. To continue more of model testing, I will pass on the ball to my groupmates to discuss further. Thank you and God bless.
Hello, good day to everyone. This is Humphrey Uchigi, and I'm here to continue the discussion on the pragmatics of model use. So one of the pragmatics of model use is replicability in terms replication. So there is a saying that repetition is the mother of physics and other empirical sciences. So trying to produce the results of other sciences is a common method of validation in other empirical sciences, because replication provides an important check that reveals errors, improves the transparency and utility of modeling work, and also uncovers the occasional fraud. However, the role of reproduction of findings for scientific progress is underestimated in the economic sciences and in the field of system dynamics. So why is there so little replication? Well, replicating and extending someone else's study is viewed as uncreative work by most researchers, and of those replications that were conducted or attempted, it is more likely that the ones are being published are those that contradict the original findings, which creates somewhat of an incentive for researchers to withhold their data from others. Nevertheless, replication is necessary to guard against ad factoring. Ad factoring allows unethical modelers to sell their mental models with all hidden assumptions while at the same time cloaking them in the authority of sciences. calculations has been somehow tampered with to make results give a misleadingly good match to experimental data. It is a fraudulent and deceptive practice even when the modeler does not keep it a secret. So another pragmatics for model use is protective modeling and reflective modeling. Now, the difference between the two is that in protective modeling, modelers cover up important assumptions using selective data to support their biases and their prejudices. This type of approach weakens the model. While in reflective modeling, it uncovers flaws and hidden assumptions and challenges and expose assumptions for critique and improvement. It also strengthens the model. So those were the pragmatics for model use, and now let's move on to the test for dynamic models. Now there are various tests for dynamic models, and I'm here to showcase some of them here today. So the first on our list is the boundary adequacy test. So based on the name, it tests if boundaries are adequate and that key variables are to be endogenous. Endogenous meaning something internal. So if your system has no controlling parameters for you to control, then the problems is maybe something external, which you have no control of. That means you cannot improve the system unless the system somehow changes externally for the better. So this is the purpose of the test, to consider the significant implications with regard to our dynamic models, if it is something we, we have control of. So the next on our list is the structure assessments test. So this tests if the structure conforms with the real system and laws of nature. So for example, when deaths occur, population has to reduce. When births occur, population has to increase. So those kinds of laws of nature has to be abided by. It is good to check all those relations within the model, and we can use this test. And the dimension and the next test is the dimensional consistency test. So this test is one of the basic tests, and it must be carried out during the construction of the model. It entails the analysis of a model's rate equation. So this test involves literally checking the right-hand side and left-hand side of each equations of the model. So the dimensions of the left hand and the right hand side of an equation should be the same for correct model formulation. So let's have here an example. This is the basic equation, the equation of force. Force is equal to mass times acceleration. So do you think the equation is correct or maybe wrong? That is the question we ask in this test. So to check the correctness of the equation, we should know what is this F, what is this M, and what is this A. So F is force. So we should check if the dimensions of force is equal to the dimensions of mass times acceleration. So that is the basic guise of dimensional consistency test. Our equation must be consistent, and the dimensions of the left-hand side and the right-hand side of the equations must be the same or must be equal. Thank you.
Good morning, everyone. I'm Junlin Orais, and I will continue to discuss model testing in practice, particularly parameter assessment, extreme condition test, and the integration error test. Parameter assessment. Before deciding how a parameter should be estimated or whether its value is reasonable, make sure every constant and variable has a clear real-life meaning. Then decide how to estimate the value of each parameter. One of the basic choices to estimate the value of each parameter is formal statistical estimation. The estimation of parameter values from numerical data receives a great deal of attention in modeling because it is essential to know how the important regression techniques work, what their maintained hypotheses and limitations are, and when each tool is appropriate. Other, more robust estimation methods are available, ranging from relatively simple maximum likelihood and GLS or the generalized least squares method to sophisticated methods such as Kalman filtering. However, it is important that you select the simplest method that is appropriate to the feedback structure of your model and the statistical properties of the data. Also, the statistical estimation has its limitation because it is impossible to estimate all parameters in a model. Also, you must develop the ability to estimate parameters judgmentally or the judgmental estimation using expert opinion gleaned from interviews, workshops, archival materials, direct experience, and other methods. Actually, in practice, statistical and judgmental methods are used together because the knowledge of the real system constrains the possible range for many parameters, while statistical estimation provides a check on judgmental estimates. Another test in modeling is the extreme condition test. This test asks whether models behave appropriately when the inputs take on extreme values such as 0 or infinity. There are two ways to carry out this test. The first one is the direct inspection, and the second one is the simulation. I have here an example of extreme condition test. This test asks what would happen to the GNP of the United States if all energy sources instantly and unexpectedly disappeared, suddenly deprived of all forms of energy. The GNP must rapidly drop close to zero. Accessing the model via a time-sharing link, the test was implemented. What was the result? The GNP went up. Examining the model equation showed that, consistent with its origin as a traditional demand Keynesian model, GNP was formulated as depending on aggregate demand. Aggregate demand consists of consumption, investment, government expenditures, and net export. The famous identity GNP equals C plus I plus G plus X. The C, I, and G were formulated as depending on factors such as consumers' incomes, business profitability, interest rates, and so on. Output of goods and services did not require inputs of energy, and a 100% embargo did little. Why then did the GNP go up? Oil imports fell to zero, so net export increased. You may object, as the model's developers did, that the test was irrelevant since such extreme condition could never arise in reality. The model replicated the historical behavior of the economy and the energy sector quite well, so they argued it was a reliable guide to their likely behavior in the future. These arguments are mistaken. The test uncovered limitations of the model that rendered it unusable, unusable for our purpose. We needed to know how a physical shortage of oil would affect the economy. A model in which production requires no energy cannot answer such questions. The energy sector had been tacked on as a set of ad hoc additions to the original model. Production drove energy consumption in the model, but energy availability had no impact on production. Lacking such basic physical realities, the only way the modelers could answer the question we posed was through still more ad hoc adjustment to model structure or ad factoring based on their mental models. The fact that a model replicates historical data well is irrelevant if it fails important extreme condition tests. Models are usually intended to design policies to solve problems, improve performance, or analyze contingencies, for which experiments provide no guide. The goal of policy design is to move the system outside the limited range of historical experience. Extreme condition tests provide a critical test of the extent to which model captured underlying physical realities and constraints that affect behavioral outside the condition observed in the past. The integration error test. This should be the first simulation test that should be carried out because failure of this test renders all model results meaningless. System dynamics models are usually formulated in continuous time and solved by numerical integration. You must select a numerical integration method and time step that yield an approximation of the underlying continuous dynamics accurate enough for your purpose. The result of your model should not be sensitive to the choice of time step or integration method. The wrong time step or integration can introduce spurious dynamics into your model. Always test for such DT error by cutting the time step in half and running the model again. If the results change in ways that matter, the time step was too large. Continue until the results are no longer sensitive to the choice of time step. Likewise, run the model with alternate integration methods. That's all. Thank you.
Good morning, everyone. My name is Marie Razel Denise Oyos, and I will be reporting about behavior reproduction tests and behavior anomaly tests. Behavior reproduction tests. Many tools are available to assess a model's ability to reproduce the behavior of a system. Most common are descriptive statistics to assess the point-by-point fit. Point-by-point metrics compute some measures of the error between a data series x sub b and the model output x sub m at every point for which data exists and then report some sort of average over the relevant time horizon. Table 21-5 lists some of the most common measures of point-by-point fit. The most widely reported measure of fit is R-squared, the coefficient of determination. R-squared measures the fraction of the variance in the data explained by the model. If the model exactly replicates the actual series, R-squared equals to 1. If the model output is constant, R-squared equals to 0. R-squared is the square of the correlation coefficient R, which measures the degree to which two series vary. The mean absolute error, MAE, mean absolute percent error, MAP, mean absolute error as a percent of the mean, MAE, or mean square error, and MSE, means it provides measures of the average error between the simulated and actual series. MAE weights all errors linearly. RMSE weights large errors much more heavily than small ones. Both measures the error in the same units as the variable itself. MAPE should not be used, of course, if the data series includes any points close to zero. In such a case, the MAE divided by the mean of the data provides a more robust dimensionless measure. Which measures are best? MSE penalizes large errors far more than small ones. Usually, there is no strong basis for preferring RMSE over MAE. The MAPE and MAE or mean provide dimensionless metrics for the error which are easier to interpret. R squared, though it is widely reported and your audience may expect it is usually not very useful. Two series with the same absolute error can generate very different values for R squared depending on their common trend. Consider the situation. X sub m equals x sub 0 exp parenthesis gt x sub d equals x sub m plus e. The data and model grow exponentially at the same rate. G and the model is perfect except for a random error, E. The higher the growth rate, the greater the correlation R between the model and data. Therefore, the higher the value of R squared, though the error between the model and data is the same in all cases. It is important to know the sources of error as well as the total size of the error. Large errors may be due to a poor model or a large amount of random noise in the data. The total error may be large if a mode of behavior in the real system is deliberately excluded as irrelevant to the model purpose. While there is ultimately no substitute for plotting the simulated and actual data together, several statistical methods help decompose the error into systematic and asystematic components. The tail inequality statistics provide an elegant decomposition of the error by dividing the MSE into three components: biased, unequal variation, and unequal covariation. Bias arises when the model output and data have different means. Unequal variation indicates that the variances of the two series differ. Unequal covariation means the model and data are imperfectly correlated, that is, they differ point by point. Table 26-6 illustrates the interpretation of the tail statistics for different situations. A large bias indicated by both a large MSE and a large bias reveals a systematic error, as seen in case A. Errors due to a bias are potentially serious and are usually due to errors in parameter estimates. Error due to unequal variance may also be systematic. When unequal variation dominates the MSE, the model and data match on average and are highly correlated, but the variation in two around their common mean differs. One variable is a stretched out version of the other. In case B, unequal variation is a large because the trend in the two variables is different. Such a case reveals systematic error and directs attention to the assumptions of the model. Systematic error is also the verdict in case C, in which the model does not capture the magnitude of a cyclical mode in the data. Though the phasing is correct, such a case would direct attention to the factors controlling the amplitude and damping of the cycle. If both series have the same mean, bias equals 0, and either the model or data series is nearly constant, then unequal covariation will be small because the standard deviation will be small. As shown in case D, the error would reflect random noise or a cyclic mode in one of the series not present in the other. The interpretation depends on the purpose of the model. If the model is designed to investigate the cycle in the data, failure to generate the cycle would clearly be a systematic error. If the purpose of the model is analysis of long-run behavior that abstract from short-term movements, failure to capture the cycle is unimportant. The cycle becomes unsystematic noise relative to the model purpose. If the majority of the error is concentrated in unequal covariation, the model captures the mean and trends in the data well, differing from the data only point by point. Cases E and F. These cases may indicate a fairly constant phase shift of a cyclical mode, otherwise reproduced well. More likely, a large unequal covariation indicates the presence of noise or cyclical modes in the data series not captured by the model. When unequal covariation is large, the majority of the error is unsystematic. A model should not be faulted for failing to match the random component of the data. The tail statistics help you characterize the source of error. Ideally, the error should be small and unsystematic. Large errors and large bias or unequal variation factors indicate systematic error and should lead to questions about the assumptions of the model. The criteria for deciding whether an error is large or systematic depends on the purpose of the model. If the error arises from modes of behavior excluded from the purpose, then the errors do not compromise the utility of the model for that purpose. Error measures such as MAP and R-squared measure the point-by-point correspondence of the model and data. There are several circumstances in which you should not expect your model to correspond to the data on a point-by-point basis. Many systems, including the supply chains and commodity markets examined in chapters 17 to 20, selectively amplify certain frequency in the random shock that constantly perturb them. Since no model can capture all the random variations in the environment, model dynamics can diverge from the data even if the model is perfectly specified. Further in the path dependence, systems small differences in random events can dramatically alter trajectory of the system, including its ultimate equilibrium. Figure 10-25 show a certain product going to dominate its market. Running the model with different random perturbations might cause the product to win sometimes and lose to the competition sometimes. The real world that generated the data can be thought of as just one realization of the process. Small differences in observable perturbations might have led to a completely different outcome. In general, the greater the extent to which the model's dynamics are driven by exogenous inputs, the greater the point-by-point correspondence of the model and data should be. The exogenous inputs, including their blips and dips, force the model to dance to a particular beat. In a model that is not forced by any historical data series, it is often necessary to excite the model's latent modes of behavior with random noise. Even when the random noise is drawn from the correct distribution, the point-by-point values will differ from historical experience and so will model output. Figure 21-1 illustrates this dynamic with two simulations of the inventory workforce model developed in Chapter 19. The system is disturbed from equilibrium by a random variation in labor productivity with a standard deviation of 5% and a correlation time of 4 weeks. These random shocks cause the system to oscillate irregularly. One simulation can be interpreted as the real data and the other as the output of the model. The model is a perfect replica of the real system, identical structure, initial conditions, and parameters. The trajectories of the two simulations are identical as long as the model is driven by exactly the same random shocks as the real system. Beginning in week 200, the random shocks perturbing the model begin to differ. The random variations are drawn from the same distribution with the same variance and correlation time, but differ point by point. The behavior of the model quickly diverges from the data. The inertia of the system causes the trajectories to remain close for only a few weeks. After that, there is no point-by-point correspondence between the model and the real system, though the model is perfect. Obviously, point-by-point measures of errors such as R-squared, MAPE, or MSE would be grossly misleading as indicators of the realism and utility of the model. Point-by-point error measures are not meaningful when the model is highly sensitive to a noise. Instead, a good model should exhibit the same modes of behavior observed in the data. Fluctuations should have the same frequencies and amplitudes. The phase relationships among the variables should be the same as observed in the data. The variability of features such as amplitude, frequency, and phase lag should also correspond to the data. The ability of a model to generate the appropriate patterns of behavior can be assessed qualitatively by judgment or statistically. Tools such as spectral analysis measure the strength of fluctuations at each frequency. The autocorrelation function quantifies the inertia of persistence in a variable. Cross-correlation function shows how one variable depends on current and past values of another. Barlas 1989-1990 describe how these and related tools can be used to quantify the correspondence of the model and data in terms of relative amplitudes, frequencies, phase lags, and other relationships. Even when you are statistical measures to assess the correspondence of the model to the data, you should always plot the simulated and actual data together. Examine the model to see if it captures asymmetries and other subtle features of the behavior observed in the data. Beware a modeler who asserts that the model's ability to fit the data indicates that the model is a valid or confirms the model. Any such assertion is logical fallacious. Behavior reproduction tests cannot prove a model is correct or reliable. To argue that fitting the data implies that the model must be correct or superior to other models commits the fallacy or affirming the consequences. There may be many models that replicate the data well. Observing that one thus can never show that the behavior of the real system was generated by any particular structure. Different models can fit a data set equally, while yet give radically different forecasts or policy results outside the historical range. Indeed, given any set of data, there always exists an infinite number of models that fit those data to any arbitrary degree of accuracy you care to specify, all yielding different behavior outside the range of experience. The proper use of the behavior reproduction test is to uncover flaws in the structure of parameters of the model and assess whether they matter relative to the purpose. Instead of showing how well your model fits, you should point out to your clients all the places it doesn't. These discrepancies mark the trails that can guide you to erroneous parameter estimates and inappropriate assumptions you should revise before using the model for policy analysis. Every discrepancy should be discussed. Those discrepancies you believe are significant must lead to model revision until you and your client agree that the remaining differences between the behavior of the model and the data do not matter to the purpose and need not be corrected. The revisions you undertake to resolve important discrepancies between model behavior and data must also be consistent with all the other formulation principles discussed above. It is not acceptable to introduce fudge factors or exogenous variables whose sole function is to improve the historical fit of the model. Doing so serves only to lull the client into accepting the model while covering up its underlying flaws. Example, capital punishment. What is the effect of the capital punishment on the murder rate? This emotionally charged issue has been the subject of many empirical studies. Often, regression techniques are used to estimate how the murder rate differs between states with and without the death penalty. Lehner, 1983, conducted the boundary adequacy test by exploring the robustness of such regressions to different set of explanatory variables. The dependent variable is the murder rate per 100,000 people, and the explanatory variables include measures of deterrence such as the probability of execution given conviction for murder, the median time served given conviction, and the probability of conviction given arrest. Of course, since the different states vary in more ways than whether they execute convicted murderers, the regression must include additional explanatory variables in an attempt to control for these other sources of variation. The choices of these notions variables is a matter of judgment, and different investigators select different explanatory variables based on their ideological perspective. Leonard selected a set of control variables commonly used in such studies, including economic indicators and social variables. Selecting different set of explanatory variables gives wildly different results, all statistically significant. A single execution could deter as many as 29 murders or actually lead to an increase of more than 12 murders. The extreme sensitivity of the result choice of a model variables left Linar with the feeling that any interference from this data about the deterrent effect of capital punishment is too fragile to be believed. Behavior anomaly tests. Data limitations often mean it is not possible to establish the significance or strength of important relationship or formulations by statistical means. Behavior anomaly tests examine the importance of these structures by asking whether anomalous behavior arises when the relationship is deleted or modified. Anomalous behavior generated by deletion of a relationship provides you with some evidence for its importance. Loop knockout analysis is a common method to search for behavior anomalies. In loop knockout tests, you zero out a target relationship. For example, in decision rules of the form correction action, you knock out the loops passing through the correction action by setting the adjustment time to an essentially infinite value. You can also eliminate loops by setting the delay times in information delays to infinity by setting nonlinear functions to, to unity for all values of x. Anomalous behavior resulting from a knockout test suggests the importance of the loop and may help establish a plausible range for the parameters and relationships. Loop knockout analysis can be revealing when the model is operating under historical conditions, but is particularly effective in conjunction with the extreme condition test. Often a loop is not active under normal operating conditions, but becomes dominant in unusual circumstances. If a loop knockout test generates bizarre or physically impossible behavior under extreme conditions, you have evidence that the relationship is important and must be included, even if it is not normally active and cannot be estimated statistically from the data. Another form of behavior anomaly test replaces a disequilibrium structure with a simplified structure that assumes a subsystem is in equilibrium. For example, perception and material delays can be eliminated in effect, assuming decision makers can easily recognize changes in the state of a system and instantly alter those states. Senge used behavior anomaly tests as a complement to economic trick estimation to show that certain disequilibrium formulations were important in capital investment. For example, assuming manufacturing firms' base capital backlogs were always in equilibrium generated implausible behavior under both historical and extreme conditions. Thank you.
Good morning, everyone. This is Carrie Valerie Palmares, and I will be continuing the discussion for model testing under Chapter 21 of our book, Truth and beauty validation and model testing. So let us tackle about family member test, surprise behavior test, sensitivity analysis, and lastly, the system improvement test. Let's go! Dynamic simulation models acquire added value and confidence when they are generic, or which means they are applicable to a family of similar situations. And this is addressed by the family member test. This is a test that asks whether the model can generate the behavior of other instances in the same class. The family member test is particularly helpful when the class of systems the model addresses includes a wide range of different patterns of behavior. With proper changes on parameters, the model should be able to represent a particular member in the family. Under these conditions, confidence is enhanced not only because the complementary systems can contribute to the complexity of the model developed for a particular member of the family, but also because the differences among the members can be explicitly identified and defined. So one example is a model of corporate growth. The model of corporate growth should not only explain why one particular company grew, but also explains why some other companies with different policies and parameters experiences failures punctuated by periodic crisis, and also why other companies are stagnant. Discrepancies between model behavior and expectation indicate that there are flaws in the formal model, the mental model, or both. The surprise behavior test is a test when a model generates a certain behavior previously unrecognized and it does indeed occur in the real system. A surprising model behavior is a behavior that is not expected by the analyst. When such unexpected behavior appears, the model analyst must first understand the causes of the unexpected behavior within the model. They then compare the behavior and its causes with those of the real system. In many cases, the surprising behavior turns out to be due to a formulation flaw in the model. However, if this procedure leads to the identification of behavior previously unrecognized in the real system, the confidence in the model's usefulness is strongly enhanced. Such a situation may signify a model-based identification of counterintuitive behavior in a social system. Since all models are wrong, you must test your conclusions to uncertainty in your assumptions. Sensitivity analysis asks whether your conclusions change in ways important to your purpose when assumptions are varied over the plausible range of uncertainty. There are three types of sensitivity. These are the numerical, behavior mode, and policy sensitivity. Let's start with the numerical sensitivity. It exists when a change in assumptions changes the numerical values of the results. For example, changing the strength of the word-of-mouth feedback in an innovation diffusion model will change the growth rate for the new product. The next one is behavior mode sensitivity. It exists when a change in assumptions changes the patterns of behavior generated by the model. For example, if plausible alternative assumptions change the behavior of a model from S-shaped growth to overshoot and collapse. And lastly, the policy sensitivity. It exists when a change in assumptions reverses the impacts or desirability of a proposed policy. The example for this is if cutting prices boosted market share and profitability under one set of assumptions but led to ruinous price wars and bankruptcy under another, the model would exhibit policy sensitivity. Sensitivity analysis requires much more than varying parameters. You must also consider the sensitivity of your results to assumptions about the boundary of the model, to changes in the level of aggregation, and to changes in the way people are assumed to make decisions. The ultimate goal of modeling is to solve a problem. The last type of model testing is the system improvement test. It asks whether the modeling process helped change the system for the better. In order to pass this test, the modeling process must identify policies that lead to improvement, and then those policies must be implemented. And lastly, the performance of the system must actually improve. In practice, assessing the impact of a model is extremely difficult. It is hard to assess the extent to which the modeling process changed people's mental models and beliefs. It is rare that clients adopt the recommendations of any model promptly or without modification. When new policies are implemented, it takes a long time for their effects to manifest. There are three keys to successful assessment of a modeling intervention. The first one is the prospective evaluation. Modeling projects should be designed with evaluation in mind from the beginning. Prospective evaluations are more effective than retrospective studies. After the fact, you may discover that the data you need were not collected. Discuss with your clients how you will know if the project is successful or not. The second one is the use of multiple data sources. Modeling interventions can change people's beliefs and attitudes, their behavior, formal organizational policies, and of course, the actual performance of the system. You should measure change in all these dimensions. Often, you will have to create instruments such as interview protocols and surveys to document people's mental models, behaviors, and changes in policies. And lastly, to the extent possible, design your intervention as an experiment. Look for opportunities to conduct natural experiments. For example, comparing the performance of the intervention to that of business units or companies that did not undertake the modeling process. Consider partnerships also with academics and others who can serve as neutral observers to document the impact of your work. And so that would be all for my report. Thank you very much, everyone, and God bless.